So one of the things you'll notice after spring break, my pen isn't quite lined up right. My writing is going to be messier than normal, which is saying a lot. I'll readjust the pen tonight sometime. Probably won't get through the whole lesson, but here we go. Friction. What causes friction? Friction is due to the interlocking of molecular hills and valleys between a surface and an object on the surface. Your lab table might look smooth to you, but Geo, when you zoom in, your lab table on a molecular level is all jaggedy, and the surface of your hand is kind of jaggedy, and as those molecular hills and valleys slide across each other, they catch each other, they interlock with each other, and that's what you feel resisting you. That's the force of friction. The key idea is this: friction resists sliding. And because of that, it can resist motion. If you push something on the floor and let it go, it slides to a stop very quickly. But it can also create motion. We said that when you walk, friction is what pushes you forwards. That's why it's so tough to walk on ice. So it can both cause motion and resist motion. It's always going to be in the opposite direction that the object. It's going to be, well, you'll see. Draw the direction of friction in each case. Let me zoom in. So here's a lovely picture. We are sliding a block. The block is sliding to the right. The motion is to the right. Friction is always in the opposite. Well, let's see. Which way would friction be acting? Now, if you zoom in, I could not get this to quite touch. Can you pretend that gap isn't there? So I'm going to go like this right now and color that in just to say, hey, they are touching. If you were pulling this to the right, the same way you pulled your hands towards you, which way did you feel a force resisting you? Which way would friction be acting? Okay. My abbreviation for the force of friction is an F with a little FR, force of friction. You can leave the R off. I don't know why, because that's also force of friction. I don't know why, Sarah, but years ago I just got in the habit of putting an R on there, so I always will. Go figure. All right. What about for a car speeding up? Well, again, friction is a Newton's third law reactive force. So if we follow this tire around, right here it's pushing backwards. Friction resists the push. Which way will friction be pushing then? The opposite of backwards. Yeah. Here, friction is what makes a car go forwards. It's the force that pushes you forwards. That's why it's tough to drive on ice, because on ice, you still have the tires, you still have the motor. Which force has changed? Friction has changed. We'll talk about why friction is so small on ice a bit later. It's going to show up in our equation. What about for a car slowing down? Well, when you hit the brakes, Geo, actually what happens is your front wheels apply a force against the pavement forwards. Forces come in pairs, so friction is going to apply a force which way? Backwards. Okay? Friction resists sliding. It's in the opposite direction that the objects try to slide. But it can cause motion. You can't always just say it's going to be in the opposite direction that the thing is moving. It can cause motion. It can resist motion. How do we calculate it? Well, friction depends on two things. The first thing that it depends on, next to number 1, can you write the word stickiness? It depends on how sticky the objects are. Is ice sticky? So, not much friction. Is Teflon sticky? No, not much friction. Is Velcro sticky? With the right surface, lots of friction. We're going to give this notion of stickiness a symbol. So, I wrote down here, it depends on the type of surfaces that are in contact, how sticky they are relative to each other. We call this, here's our word of the day, phrase of the day, the coefficient of friction. And it has a symbol. The symbol is the Greek letter mu. It looks like this. It looks like this. Here's a mu. It sort of looks like a lowercase m with a long tail. And it's where our lowercase m comes from. This symbol, we call it the coefficient of friction. It's a number that describes how sticky two objects are relative to each other. The bigger the number, the stickier they are. The closer to zero, the slipperier they are. Ice has a coefficient of friction of about 0.01, especially steel on ice skates. Rubber on concrete has a coefficient of friction of about 0.75. The closer you are to 1, the stickier you are. When you're above 1, that's glue. Seriously, that's like, oh, it can handle its own mass and hold something else as well. Okay. It has no units. What are the units for mu? Nothing. It's a ratio, and I'll show you why it has no units later on. It's a dimensionless quantity. It's just a number, a decimal, typically between 0 and 1. If mu is large, there's lots of friction. If mu is small, there is little friction. So steel on ice, about 0.01. Rubber on concrete, about 0.75. Rubber on rain, it drops down to about 0.4, so slow down when it's raining. Rubber on ice, it drops down to about 0.1, so slow down when you're on ice, really slow down. The second thing it depends on, well, this we have to think about. Is it easier to slide a lighter object across the floor or a heavier object across the floor? Lighter object. So you might say it depends on mg, except somehow I have to explain one more thing. I'm going to keep the recording going, but I'm going to walk away from the screen. I'm going to pick on Sasha's table here. If I push on Sasha's table right now, is it accelerating? Everybody say no. Am I applying a force on it though? So that must mean there's a force back at me. That's friction. And it's exactly as big as I'm pushing. If I'm pushing with 12 newtons, you know how big friction is? Restart required. I'm not going to restart now. 12 newtons. If I'm pushing with 14 newtons, you know how big friction is? Now suppose the biggest friction can be is 15 newtons. If I push with 15.1, it must accelerate because now I have a 0.1 unbalance. Okay with that? But you said heavier objects are tougher to slide across the floor than lighter objects. But I want to just look at this object. So if I push, is it moving? Is it accelerating? I'm going to push with the same force. I'm going to pull. So I'm going to pull towards me. Is it accelerating? I'm going to pull with the same force, but I'm going to lift up as I do so. What happened? Did gravity change? Did the mass of the object change? What force changed in the free body? What? Friction depends on two things. It depends on how sticky the objects are, the coefficient of friction, mu. What does a Greek cow say? Mu. Oh, whatever. What does a Greek cat say? Mu. There's all sorts of dumb jokes that go along with that. But it also depends on not how heavy the objects are, how hard the ground has to push up against the object, and that allows me to do three things. Number one, I can lift up. And that makes it easier to slide. If you've ever tried to move furniture, you figured that out. I can just pull straight, or I can be really dumb. I can push down and try to slide it. I'm really increasing. I'm pushing pretty hard at you guys, but I'm increasing the normal force so much, the friction is so big, I'll probably never be able to overcome it. Friction depends on two things, Connor. Mu, stickiness, and the normal force. So I wrote down here, depends on two things. The force pushing the surfaces together is the second one. And what we call that the normal force. Now, sometimes if nothing else is pushing up or down, Zach, the normal force will be equal to mg. And in physics 11, that'll often be the case. In physics 12, is the normal force equal to mg very often? Hardly ever. Okay? Here is our equation. We can put it in the box down here. This is on your formula sheet, but we'll write it out. Friction is equal to mu times the normal force, where mu is the coefficient of friction which I'll tell you in the question. The normal force, we'll have to figure out because I don't have an equation for the normal force. And that'll let me calculate friction. So let's look at example 2. Here's a bench below. In fact, you know what? The benches in the gym, at the back of the gym, the ones that you slide around, let's do those, okay? So consider the bench below, which is being pulled by student number 1 across a rough surface. Rough surface means there's friction. That's my code. If I say ice, usually I mean no friction. At a constant speed, if I'm at a constant speed, it means the forces are balanced. Suddenly, student number 2 pushes down on the bench. You know what? Let's even say this. Student number 2 comes along, because I'm sure you've seen this happen, and sits on the bench while someone's trying to slide it. Okay? It says, if student number 1 maintains a constant force, what happens to the weight, the normal force? You know what? Let's call this part A. Let's put a B above normal force. Let's put a part C above friction. Let's put a part D above motion of the bench. So Tato is pushing the bench across the floor, and then he's keeping it going at a constant speed. Gio comes along and sits on the bench. What happens to the weight of the bench? Now, what was weight a synonym for? The force of what? Gravity, the mg. Does the mass of the bench change? Does the mass of the bench change? No. So does the weight of the bench change? Does the mass of the bench change? No. And if weight is mg, did the m change? No. Did g change? No. Did the weight of the bench, I'm not talking about any other forces, just the bench itself, did that change? So I'm going to say this. mg is the same. And this is why, Zach, when you said, yeah, it's tougher to push heavier objects, I had to say, but we have to somehow explain why it's easier when you lift up. What happened to the normal force? Well, let's add let's add our free body diagram. So right now we have mg down. But because Gio is also pushing down, is this bench sinking into the ground like quicksand? Is it flying into the air like Superman? So the forces have to be balanced. But now, since there is 2 forces down, the force pushing up, the normal force, must be something like that. So what happened to the normal force? My abbreviation for increased is an arrow pointing up. Guess what my abbreviation for decreased is? Yep. Guess what my abbreviation for same is? Apparently SAME. I haven't got an abbrev for that one. So the weight didn't change. The normal force is what changed. So what happens to the force of friction? What did we write in the box? Friction equals what times what? Mu times the normal force. If normal force gets bigger, what happens to the force of friction? So now, instead of in the first part, friction and the applied force being identical because it was constant speed, friction just got bigger. So what's going to happen now? Who's winning? So bench slows and then stops. The only thing is this: friction will not do work for you. In other words, friction is only as big as it needs to be. As the bench slows down, friction gets smaller and smaller and smaller, and when the bench stops, friction is also equal to 0 right then. It matches you exactly. Okay? It says, explain your answer using principles of physics. We just did. Is that okay, Gio? This is why you're going to hear me say friction is what times what? It's mu times the normal force. Friction is what times what? It's mu times the normal force. Let's do some with actual numbers here. Oh, thought experiment, first of all. Turn the page. A student gives an old shopping cart a big push on a flat, rough surface. When I say rough, what I'm really trying to say to you is, I think there's going to be friction involved here. Which of the following is the best force diagram for the cart after the student has released it? You know what? Once again, we get to vote. Once again, how you hold your hand up is how sure you are of the answer. Which of the following is the best free body diagram? Now, let me show you what I mean. Look up. My floor isn't very rough, but it's kind of rough. We'll use a chair instead of a shopping cart. And what I want you to think about is what the best free body diagram is the split second I let it go. Ready? I want the free body diagram right there, right there, right there. But not when it stopped. 1 second before that. Which of the following do you think is the best free body diagram? Looking at A, B, C, or D. And, oh, the motion is to the right, so we've given it a push to the right like I just did for you folks. All right? Who says it's got to be A, Mr. Dewick? I go with A. 1, 2, 3, 4, 5, 6. Matt, I don't know whether that's a wimp out vote of yes or you're scratching your chin because you literally went like this. Are you voting A or no? Okay. And Nick, is that 8? 9? Or is that a German saying no? 9? Oh, sorry. Who says B? 1, 2, 3, 4, 5, 6, 7. Ooh, 8, 9, 10. This is a good question. We've got a controversy. Who says C? Who says D? 1. Gio looked around. Did you vote? Did you vote? Yeah. Eric, you did? Saki, did you vote? Which one? A, B, C, or D? B? Not saying she's right. Sorry? You were for D? Okay. Convince me. Are you attacking someone else's answer as being wrong, or are you defending your answer as being right? You'll defend A. Convince me. Oh, okay, hang on, let's do this again. There's the push. It's slowing down. I'm going to phrase that slightly differently. Which way is it accelerating? That way. Which way must there be an unbalanced force then? So this is the usefulness of Newton's first law. So just with that, which diagram must be wrong? Which diagram doesn't have an unbalanced force pointing to the left? It gets rid of C and D. And doesn't it also get rid of B? There's only one diagram there that has the ability for this chair to slow down. From Newton's first law, there's only one diagram there, Gio. And I love the way you handled it. You said, which way is it accelerating? That tells me a lot. That tells me which way the unbalanced force has to be. Have I convinced the rest of you? 9 of you were okay. Some of you were just still guessing there. It's got to be A. Oh. Newton's first law. And if you want to, you can say the unbalanced force, I'll make this bigger in a second, must be left to the left. Bracket slowing down. Let me make that larger. Another thing I forgot to change was the default font on this thing. I'll have to do that. There. Is that big enough? You can read it back there okay? Yeah? Newton's first, very powerful. There's a tricycle in your future that you'll laugh at someday. Rylan is smiling, but don't give away the punchline. Okay? All right. Let's start walking through calculating the force of friction. So it says this. Find the maximum force of friction between the mass and the ground for the following objects. We're just going to assume that we're pulling to the right, but it's not moving. How do I calculate friction? Well, we said this. Friction is mu times the normal force. This is a job for a free body diagram. In fact, anytime you're dealing with friction, you're probably going to want to do a free body diagram. Although, I'm going to cheat. Since they gave me the picture, rather than representing the mass with a dot, don't do that. Let's label the forces right on here. Let's just label them right on here. What are the forces acting on this box? Get the obvious one. Gravity. Good. Is it sinking into the ground like quicksand? Is it flying into you like Superman? So what else must be acting on this box? How big? The same size as gravity. What did this question ask me to calculate? The force, the maximum force of friction. Friction is what times what? I don't know the normal force. Oh, but look. I know another force the same size as the normal force. See my free body diagram? What force has to be the same size as my normal force? So for this situation, I can say friction is going to be mu times mg because the normal force is the same size as mg. What's mu? I don't know. What's mu with you? What's mu? I wrote it in the question. I just drew an arrow. What did I say the coefficient of friction was? Yeah, Sasha? 0.35. 0.35. Your sneakers on wet pavement when it's slippery-ish, but not crazy slippery. Okay. And M8G 9.8. In this situation, the maximum the force of friction could be 0.35 times 8 times 9.8, 27.44. Units, it's a force. Newtons. Let's compare that with situation B. What are the forces acting on this block? Get the obvious one. Is this block sinking to the ground like quicksand? Is it flying into you like Superman? So vertically the forces must be balanced. Why would I take marks off if you said the normal force, don't write that down, if you said the normal force was the same size as mg? Why is that impossible here? There's another 55 newtons pushing down. So if I asked you, and this would be a good little test question to draw the free body diagram on this, what I'd really be looking for is a normal force larger than mg. Nathan, what does this question want me to find? The force of? Okay, friction is mu times what? Times the normal force. I don't know the normal force. Oh, but look. I can figure out the normal force. Do you see it? Is this, Nathan, is this box sinking into the ground like quicksand? Is it flying into you like Superman? What that really means is forces are balanced, or everything up equals everything down. Everything up equals everything down. What's the only force pointing up? Equals, what are the forces pointing down? And would that be plus? As a number? Yep. When I showed you the normal force earlier this year, Pierce, I said to you, I will never give you an equation for the normal force. I don't know that there is one, but I can always figure out how big it has to be because I'm not sinking in the ground like quicksand. I'm not flying it like Superman. Or if I am, I'll put a scale in the question and I'll tell you something about the scale because the scale measures normal force. So this is going to end up being 0.35 bracket mg plus 55. Gio, what was the mass of this object? 8. What was g, folks? 9.8 and not negative. In this unit, we're letting positive be whatever's convenient. So 0.35. This is where you want to see if your calculator will let you do nice brackets like this. This is part of why I've gone on my calculator rent. 8 times 9.8 plus 55. Friction should be bigger than 27.44 because it is tougher to slide something if some idiot friend is pushing down on it or sitting on it. You get 46.7? Yeah. Now, let's suppose I pull on this with 40 newtons. Will it move? No. How big is friction? 40 newtons, not 46.7. Friction will always just match me. Let's suppose I pull on this with 42 newtons. Will it move? How big is friction? 42 newtons in the opposite direction. The reason I know the forces have to be balanced is it's not accelerating. What if I pull with 46.6 newtons? Will it move? What if I pull with 46.7 newtons? That's that magic point when you can start to feel something, start to give, and then if I pull with 46.8 newtons, it'll accelerate my way. But I do want you to realize that friction is only as big as it needs to be. If friction was always 46.7 newtons, that would mean if I tug this way with 10 newtons and then let go, it would knock you guys over because 46.7 newtons this way, 10 newtons this way, that would leave 36 newtons. It would have to accelerate that way. It doesn't do that. So one of the other weird things about friction, Wild, is it's only as big as it has to be. It's going to match you as long as it can, and then once it can't match you, it'll be at its maximum. Okay? Do I have a part C? I can't remember. Oh, I do, lifting up. Let's do our free body diagram here. What are the forces acting on this? Get the obvious one. Is this mass sinking into the ground like quicksand? Is it flying through like Superman? No, so the forces vertically must be balanced. Why would I take marks off if you drew the normal force exactly the same size as gravity? 55 newtons of the normal force somebody else is taking care of. So the normal force here is going to be smaller than gravity, and I always try and exaggerate it so I really notice what's going on. I'll go roughly to scale, but I want to make sure it catches my eye. This question wants me to find friction, so friction is mu times the normal force. I don't know the normal force. Oh, but look. I can figure out the normal force from the free body diagram. Nathan, everything up equals everything? So what are the two forces pointing up? Let's write that over here. Normal force and 55 equals everything down. How would I get the normal force by itself here? How would I get the Fn by itself here, folks? Minus what? Yeah, minus 55. Is that okay? The normal force in this case is going to be mg take away 55. So over here, friction is going to be mu 0.35 mg take away 55. If you're lucky, if you're clever, if you have a decent calculator, you might be able to just backspace or back arrow, and in this case, change the plus sign to a minus sign. I wonder if Jason's calculator can do that. 8.19, 8.2. I'll go 8.19 newtons. So, to get diagram A accelerating to the right, you would need to pull with more than how many newtons? 27.44. To get diagram B accelerating to the right, you would need to pull with how many newtons? With more than how many newtons? 46.7. And to get diagram C accelerating to the right, you would need to pull with more than how many newtons? 8.19. Okay? This takes care of all of the ways I can think that friction behaves. Max, definitely friction depends on the surfaces. Ice is easier to push or slide on, so that's the mu component. That's what takes care of the surfaces. And it depends on sort of how heavy the objects are, but I want to somehow take into account the fact that when I lift up, it's easier to slide. That's the normal force, which does depend on how heavy the object is, but any other vertical forces that are in there too. Is that all right? So let's put it all together. Example 5 says, for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, and find the acceleration. In fact, you know what? I think we can go draw a line right down the middle of the page here. Like that. Before we go further, let's do a free body diagram. Well, you know what? Rather than do a separate free body diagram, Brees, let's just label our forces. Brees, what are the forces acting on this block? Get the obvious one. I agree. Is this block sinking in the ground like quicksand? Is it flying into like Superman? So what else? And I think in this case it's the same size as gravity. I did a quick check. I don't see any other vertical forces. Yes? What else? Well, there's that 20. See it? We're going to give that force a special name. This is the mystery person that I didn't bother writing. Someone's pulling on it. Our generic term for something's pulling on it, we call it the applied force, and I typically abbreviate that F applied. Oh, something's pulling on it. Geo, it could be a person, could be a horse, could be a machine, I don't care. Something's pulling on it. So which way is this block sliding? To the right. Which way would friction be pointing then? To the... Do I know there's friction? Because of that. That's my code speak in a picture. Okay? Will I put friction bigger, smaller, or the same size as the 20? My gut right now, Brisa, is that the 20 is winning, so I'll draw friction shorter. I think those are the 4 forces acting on this. Okay. Sarah, what did part A want me to find or write? A vertical force equation? Is this mass sinking into the ground like quicksand? Is it flying into like Superman? That means vertically the forces are balanced. Or, as I mentioned earlier, everything up equals everything. That's your vertical force equation. What's everything up? Yeah, more specific. Which force is everything up? Look at my picture. Okay, yeah, like that obvious. I guess normal force equals what? Yes. Gio, what's B want me to find? It's on your sheet. I've scrolled down.
Oh, wow. Find the force of
Friction. Here's our new equation. Friction equals what times what? Do you remember? Or you might have to go look at the box on the previous page. Or it's on your green sheet. Friction equals what times what? Times? Find it on your green sheet or find it in the box on the previous page. Mu times the normal force. Good. What's mu? I don't know. What's mu with you? No, wait a minute. In this diagram, what's mu? More specific. No, it's not the force of friction. Mu is not a force. What's mu? 0.12. Yeah. So friction is what times what? Mu times the normal force. Say that. Mu. Again. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Sarah, which force is the same size as the normal force? So in this case, I can say it's going to be mu mg. Gio, what'd you say mu was? No, what'd you say mu was as a value? 0.1. Good. M, what's the mass, Gio? Good. See where I put all this stuff in the diagram now, right? G. You know this. Yes. There you go. Oh, I can do this in my head. Sure I can. 9.8 times 10 is going to be 98. 98 times 0.12, it's going to be 9.8 plus, 19.6. 10.8, 11.76? And it's a force, so that's newtons. Okay? Kath, what does part C want me to do? Write a horizontal equation? Oh, see your picture? Who's winning? Oh, I like that. F applied. Who's losing? Minus friction. What does that always equal, winner minus loser? MA. Yeah. And F applied is 20, I think, right? Friction is going to be 11.76. But for now, I got it set up. Cool. And what does part D want me to find? Oh, how would I get the A by itself? Yes. This is why I've taught you all these generic ways. Rather than memorizing a different method every time, we can say, hey, I can get the A by itself. So if I hear you correctly, can I write the A first if it's okay? You're telling me it's going to be the applied force minus friction, and you said divide that whole mess by what? You'd be correct. And what was the applied force as a number? Was it 20? Was it 20? Minus 11.76. Geo helped us calculate friction. Divided by, what was the mass? Oh, I can do this in my head. It's dividing by 10. 20 take away 11 is 9. Take away 0.76 is 8.3, 8.24. 0.824? Double check me. Yes? Is that right? Oh, by the way, is this a fraction? Brackets around the top? Yes, you remember all that stuff? It is 0.824. And it's an acceleration. Units. I've mentioned that it's worth memorizing units. Yes? Okay, good. Will this accelerate? Yep. How fast? Oh, by the way, now if I wanted to, and I didn't, but if I told you that VI was 0, I could say how long for it to travel 12 meters. Find T. You know acceleration, you know VI, you know D, you can find T. Or I could say if it travels for 18 seconds, how fast will it be traveling after 18 seconds? You can find V final now. All the previous stuff is fair game. Let's do a free body diagram for this second diagram here. Okay. Max, what are the forces acting on this block? Get the obvious one. I agree. Is this block sinking to the ground like quicksand? Is it flying you like Superman? Why would forces must be balanced. Why would I freak out if you made normal force the same size as gravity in this case, though? There's another vertical force. So since two forces are pushing down, I think the normal force has to cancel out both of them. So I'll exaggerate it kind of like that. There's my vertical forces. What else? We still have this mystery applied. I have no idea what it is, but I just know something's pulling it to the right, the applied force. So which way is this box trying to slide? To the right. So which way will friction be pointing? To the? Good. Is that okay, Jason? Jason, what does part A want me to find? Write a vertical force equation. Okay. Are we sinking into the ground like quicksand? Are we flying into the air like Superman? So everything up equals everything down. Can you make that an equation, please? Everything up. Thank you. Equals everything down. And there's another downward force. Look at the picture.
Oh.
Yeah. Yeah. Huh? Don't overcomplicate it. There's another downwards force. How big is that downwards force? Yep. There's my vertical force equation. Connor, what does B want me to do? Friction is what times what? Geo? Friction is what times what? What times what? Mu times the? Yes! Do I know mu? What's mu? I don't know. What's mu with you? At 0.12, it's the same surface. I don't know the normal force. Oh, but look. I have an equation that tells me how to calculate the normal force. Jason did that for us. Is that okay, Connor? So I put all this together. I'm going to get 0.35 times mg plus 15. Let's plug in all the numbers just so we know what the heck we did. It's going to be 0.35 10 times 9.8 plus 15. Do that one in your head, Mr. Dewick. Sorry, hang on. 0.35, that's the last question. 0.12, I'm sorry, folks. It's 0.12, right? What's mu? 0.12. 0.35 was the last question. I apologize. That was dumb. Well, 10 times 9.8 is 98, plus 15 is 113. Yeah, I can do this in my head. It's going to be 11.3 plus 2.26, 13.56? Yeah. Units, Connor, it's a force. Yeah. Newtons. By the way, you'll notice we got a bigger force of friction because pushing down on something does make it harder to slide. Bigger than 11.76. Now, what if this had been bigger than 20? Then I would have revised my diagram and I would have said, this thing isn't moving. Not going anywhere. You haven't overcome friction yet. Eric, what does part C want me to write? Okay, who's winning? Who's losing? What does that always equal? You'll notice, Eric, my friend, it's exactly, sorry, F applied, it's exactly the same equation as CAF gave us. What has changed CAF is how big friction is, so that little subcomponent has changed, but the physics is still the same. It's a tug of war between those two forces. Ange wants me to say get the A by itself. How? Divide by? Again, it's the same procedure you gave us. We're just tinkering with the situation. So if I hear you correctly, and I think I do, you're telling me A is going to be the applied force minus friction all over the mass. In fact, it's going to be, what was the applied? 20 minus 13.56 divided by 10. Again, dividing by 10, I can do that in my head, piece of cake. 20 take away 13 is 7, take away 0.5 is 6.5, to 6.4, 0.644? It's an acceleration, boys and girls. Units? Meters per second squared. Okay. Friction. Turn the page. I'm going to go a little technical here because as a physics nerd, I have to explain things correctly, but then we're going to ignore the technicality. There is actually two types of friction. I'm going to pause the video for just a second. There can be friction on an object even when it's at rest, since the hills and valleys will lock up when we apply even a small force to an object. The force of friction on an object at rest is called static friction. Static means not moving or changing. So here's our thought experiment. Suppose I pull on a desk with a force of 2 newtons, and the desk does not move. Which of the following is true? A, static friction is bigger than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, there is no static friction. You know what? We get to vote again. Once again, how I hold your hand up, I'm sure you got the answer. Say what? Who says A, static friction is bigger than 2 newtons because it's not moving? 1, 2, 3, 4, 5, 6. Pierce just went up at the last second. Who says B, static friction is exactly 2 newtons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Pierce votes twice. Who says it's less than 2 newtons? Who says there is no friction? Convince me. Yeah. Are you attacking someone else's answer or defending your own?
I'm defending.
What did you vote?
B.
Convince me.
Static friction is 2 newtons because the desk is not moving anywhere, and so there's balance forces with friction being the balancing force from pushing it.
It's not moving. A is 0. Therefore, Newton's, in fact, if you wanted the short version, Newton's first. Okay? Now, Tato, if I pull harder and it doesn't move, then static friction will be as big as it needs to be. Maybe it can be bigger than 2 newtons, but I'm telling you, if it's not accelerating, the forces must be balanced. Okay, explain your answer. I think we just did here. So static friction acts when you have two objects at rest relative to each other. It's what keeps a car stationary with its parking brakes from sliding down a hill when it's parked on a hill. The tires are pushing against the pavement pushes back against the tires, they're in equilibrium, they're in balance, no acceleration. A block of wood will remain stationary on a ramp, but as you increase the ramp, making it steeper and steeper and steeper, eventually the block of wood will start to slide, and that moment is when static friction turns into kinetic friction, sliding friction. Sliding friction is always a little bit less. We think this is because you kind of have to break the welds or break the molecular. Well, how many of you have ever driven on a gravel road that had lots of pothills before? Okay? If you go really, really, really slow, you feel every single pothole. But if you go a little bit fast, you notice the ride smooths out a little bit, and it's because your tires don't have a chance to fall all the way into the pothole, and so the road, it smooths out. It's the same with kinetic friction. Once you start the object sliding, those molecular hills and valleys don't have as much time to completely interconnect the way they do when they're at rest with each other. Does that make sense? Okay. However, to keep the math nice, I'm going to treat both types of friction as the same thing. Even though in real life, technically there's two types of friction, I'm going to say, so, Geo, friction equals what times what?
Mu times normal force.
Where mu is the, in English, coefficient of friction. It's not a force. It's not a force. And the normal force equals? No, never. Don't ever say that again. Instead, draw a free body diagram, and then everything up equals everything down. Tato, it'll only be mg on boring questions. I got a bunch more questions to do. We're going to do those next class. We're going to pause here. I'll come back to this. Got a video to show you.